Okay, so we're covering chapter 4, this part. So let's talk about just chapter 4 in general and just this section of the course in general. These are applications of the derivative. So from chapter 3, we know all about how to take the derivative of just about every function we could possibly think of. And so now we want to apply that, applications of the derivative, to different problems. Okay, and so um, we've already seen one application, and that was actually section 3.10, where we did linear approximations. And that's a really big application of the derivative. Um, you see that in physics quite frequently, where we replace a funky nonlinear function by just a tangent line. And so it's a lot easier to analyze what happens with a tangent line than it is some weird function that you're not familiar with. Okay, so in 4.1, we're going to be looking at maxes and mins. Okay, and later on in the chapter we'll be looking at some other things, but this is kind of where we're going in this section of the course. So let me give you a quick overview of 4.1 before we actually get into it. What we're going to do here is we're going to define some new terms. So definitions will define what it means to have an absolute or global. Those words are going to mean the same thing. Max and min. We'll also define what it means to have a local or relative max and min. We'll also talk about what is an extreme point. Okay. We'll also talk about what it means to have critical points. And then there's going to be a few theorems and a few techniques. And so the theorems that we'll look at in this section are the first one is the another value theorem. This time it's the extreme value theorem. Do you remember what the value theorem was before? Well, I'll talk about it later. Its abbreviation is IVT. Do you remember what that one was? Okay, the second theorem we're going to talk about is Fermat's theorem. Whoops, Fermat's theorem. And this is not the Fermat's last theorem that was the famous unsolved problem in mathematics that was recently solved. Well, recently. Has it been recent? Recent in my mind, but I'm an old man. Fermat's theorem is kind of a big one. It sets up the stage for what we're going to do. We're going to look at a theorem that has to do with a local max or min. So local max min theorem. I should just be labeling these by the number in the book. And then the last thing we're going to be looking at isn't really a theorem, it's a technique. It's the closed interval method for finding maxes and mins. Closed interval method. Okay, and so this is what we're going to talk about. So it's really not a very big section, but it's got huge implications. So talking about maxes and mins, let's go ahead and just maybe look at a graph of one first. So let's just graph a function here, and we'll make our function be nice and continuous. Okay, so there's our function, x and y. Guess I could have made that a little nicer. All right. So what's the max? Well, the max has to do with the y coordinate, right? So the highest value on the graph is the maximum for your function. But you might say, are we looking at the entire domain? Or does the domain over here creep up? And so do we get a higher value somewhere else? And so this is where we get to the distinction between what we might call a local max versus a global max. Global max. My voice went out. So let's go ahead and define this. So what should we? How should we define this? The function f of x has a global maximum at x equals a if what we're going to write down here is that f of a is the biggest number. Or we can write f of a is greater than or equal to f of x for all x in the domain. So that's what makes it global, is that we're making this true for all x in the domain. Good. So by the way, we note, you might be hearing the word absolute. Absolute is going to be synonymous here. With global in our case. Well, that's not true in general, right? Yeah, okay. Maybe I should write it this way. Absolute max is going to be equal to global max. That's what we mean. I don't want to say that absolute's the same as or synonymous with global, because that's not true generally speaking. Okay. Anyway, enough of the semantics. So when you see the word absolute, that'll mean global. Okay. So how would you define a global minimum? The function... In fact, let me pause this and write down the definition so we don't have to spend a lot of time watching me write. Okay, so let's read through this global min thing here. The function f of x has a global min at x equals a if f of a is less than or equal to f of x for all x in the domain. Now I would point out here the equal sign that you see here in our definition. Therefore, the absolute max does not have to be a unique y value, right? Because the same y value may be hit at several different points. So, for example, in my graph over here, I might have a function, whoops, I didn't want the whole thing to disappear. I might have something like that, right? And so in this case, I have 2 points that are my global maxes. And in fact, do I have a global minimum in this situation? I do not. So I guess I should have been pointing at global max. Well, you see what I mean. So global max could be not unique as well. Okay. All right, so that's the global or absolute max or min. I usually use the word global instead of absolute. Okay. So now there's another interesting point here, and that is what happens, whoops, sorry about that. What happens if I'm looking at this picture and I'm only able to see, like this much of the picture? Oh, you can't see my fingers, can you? Let me pause for a second. Okay, so what I'm trying to say here is that suppose I only know the function locally, right, in this green box, and so I rewrote the function over here off to the side. I'm saying, this may not be the absolute or global maximum, but it certainly is a maximum on this interval, the x's that I'm looking at, and so that should also have a title, and it does, and that is called a local max. Okay, and so let's go down here and define a local max. The function f of x has a local max or min. We'll go ahead and do both of them at the same time. If there is an interval maybe I should be explicit here, open interval. We'll see what the deal is with that in just a second. Open interval about x equals a such that f of a is greater than or equal to f of x for all x in the interval. Okay, notice that that's different here. Before it was all x in the domain, and now it's all x in the interval. Good. So what would the min be? For the min, it would just be f of a is less than or equal to f of x, and then for all x in the interval. Okay. And so by this definition, by the way, I'm going to make a little note here. In this picture, you may be tempted to say that it looks like there is a local minimum here, but because we need an open interval, by open, does everybody know what I mean by open? Open interval means that it's an interval without endpoints. Okay, so it's an interval with open endpoints. Okay, so in this case, right, we would not say that an endpoint is a local maximum or minimum. So because we need an open interval about our point, we can't get an open interval at an endpoint. So therefore, a function cannot have a local max or min at an endpoint. And that is by definition. We're excluding endpoints. Okay, I'm out of time right now, but you'll see where we're going here. I think what we've done so far is we've just actually gone through our definitions. We've defined what a absolute or global max or min is. We've talked about a local max or min. Next, we'll talk about extreme points and critical points. Those will go a lot faster. And then we'll get into the theorems. All right, and then we'll do lots of examples. So see you in the next video.